Hey class, here's an example problem covering the concepts from both Chapter 7 and Chapter 8. What we have going on here is we have this 2,000 kilogram elevator that is going to be in not in free fall, it's going to be moving at 4 meters per second, and let's assume that the cables are breaking. So you're being asked by the makers of this elevator to come in as an engineer and help them create an emergency safety system. So they say at maximum, the cart or the cabin of the elevator is going to be moving at 4 meters per second when it gets to the position of your spring. They tell you also that there's these safety clamps, but they're only able to produce 17,000 newtons. Some quick calculations tell you that that's not enough to stop it, because they want it to stop safely over a distance of just 2 meters. Otherwise, it's going to hit the ground and be dangerous to the people inside. So what they've proposed is that you implement a spring down here as a secondary emergency braking system of sorts to try to stop it. And what they want to know is, what size spring do you need? What spring constant is needed to make sure that it stops in 2 meters when moving at 4 meters per second? All right, so kind of a silly problem, but very good for understanding the physics of conservation of energy. So as you can see, let's just make sure we don't forget, K, the spring constant, is what we're trying to find. So if you notice, I have a little picture here. I've labeled some forces. I've identified some point that we're going to call point 1 and some point that we're going to call point 2. And I've labeled a few variables, but we're going to need to label more. So since this is a conservation of energy problem, we must start with our conception of energy, right? Conservation of energy, which tells us that whatever kinetic energy we have at point 1, plus whatever potential energy we have at point 1, plus any work done by non-conservative forces will be equal to whatever kinetic energy we have at point 2, plus whatever potential energy we have at point 2. All right? So let's take it step by step, identifying variables as we go. So starting with point 1, do we have kinetic energy? Yes, we have a velocity. So we have 1/2 mv1 squared. And let's just write down our variables. So we know m is equal to 2,000 kilograms, and we know v1 is equal to 4 meters per second. Okay, now what about potential energy? Do we have any potential energy at point 1? Yes, we have gravitational potential energy, right? But gravitational potential energy confuses people, right? It has H, right? So what is H1? Where's the bottom? Well, you define a 0 point. So I'm going to go ahead and define this as my 0 height. And so H1 would be 2 meters above that. So you're going to have mgh1, where h1 is 2 meters. Is there work being done by non-conservative forces? Let's look here. We got gravity. Oh, that's a conservative force, so we don't have to count that. And we have this friction force. Oh yeah, friction is non-conservative. So the force of friction, 17,000 newtons. Yep, we have work done by friction. And notice it's up while your displacement is in the downward direction. So guess what? Negative, don't forget. Negative force of friction multiplied by the distance that it's moving. So our distance we'll label 2 meters, same as H1. Okay, oh wait, I forgot to check one thing. I did potential energy for gravity only, but what about elastic potential energy? Is there any elastic potential energy at position 1? Well, it's before we hit the spring, so no. Phew, okay, I didn't miss it. That was close. So that's our total initial energy right there. The kinetic energy, the potential energy, and then we have non-conservative work. So that will be equal to our final energy. Do we have final kinetic energy? 1/2 mv squared. Let's see. It comes to rest. V2 equals 0 meters per second. So no, this is 0. That's nice. Do we have potential energy? Well, the gravitational potential energy, H2, that's 0. So no, we don't have that. Some people just want to put a 0 then, but no, wait. What about elastic potential energy? Yes, we have elastic potential energy, 1/2 kx squared. Maybe I'll say x2. What is x2? It's the amount the spring is compressed, which is also 2 meters. So if you notice, h1 d and x2 are all the same 2 meter distance. So now we've labeled all of our variables, and the only thing we don't know in this whole thing is just k. So we can do some algebra to solve for k, bonus. So I'll multiply through by 2 to get rid of that 1/2, that 1/2. So now I have k x squared equals 2mv1 squared. Nope, just kidding, the 2's not there. Huh, it canceled with the 1/2, that was close. So we got, oh, okay. We have mv1 squared plus, now here's where the 2 goes, 2mgh1 minus 2 force times the distance. Now to solve for k, we have to divide by the x squared, so k is going to be equal to all of that, mv1 squared plus 2mgh1 minus 2 force times distance, d all over x squared. So from there we can just plug and chug, right? Our m is 2000, v1 is 4 squared. I'm just going to put my units, I know it's going to come out to newtons per meter, plus 2 times the mass again, 2000 times 9.8. I didn't leave myself enough room. Multiplied by h, which is 2 meters. And so again, I'm running out of room, so this is just not looking good. So I'm going to move down below here and calculate it where I have a little more space. So we erase all of that. All right. Scroll down. So now let's take 2. Okay, so we got k equals 2,000 kilograms times 4 meters per second squared plus 2 times 2,000 kilograms multiplied by 9.8 meters per second squared multiplied by 2 meters minus the 2 times the force of 17,000 newtons multiplied again by 2 meters. And all of that, oh boy howdy, that's long, divided by the x distance of 2 meters squared. You plug and chug, and if my calculations are correct, it should come out to approximately 10,600 newtons per meter, or you could write it as 10.6 kilonewtons per meter. So boom, that is most definitely box worthy. So that's a good tricky problem, but you can really see how all the different parts and ideas of energy come together in one simple equation to solve. I love energy problems. I hope that helped. Let me know if you have any questions.